And as you know, a lot of academic activities there globally. Many universities have introduced photonics programs. For example, for our students who want to take up higher studies abroad or so, there are n number of universities offering courses on photonics. In India also, many colleges. I think here also, of course, fiber optic communication course is very common in many universities now in India also. But some universities are introducing courses on photonics and now into quantum also. Then there are not national programs. Almost every country has got their national program on photonics. So in India also there was a national program starting about 2012 or so, and several universities, groups and universities are working on photonics applications. One important difference we would like to make. See, a lot of emphasis is there on the basic technical education. So most of the colleges, they are interested in imparting maybe BTech and little bit up to MTech degrees, but not so much into the R&D. That's where we are falling behind. I hope in the near future, every one of us will contribute more and more to R&D towards the progress of photonics technology, both nationally. Of course, we would like to contribute globally also and collaborate with them. Let's get going. That is brief talk about the photonics. So let us get back to the quantum information technology. As I said, the keyword is quantum. I'll elaborate more and more on that. And in simple words, as you know, about more than a century old now, that the modern technology, modern science that we see about the quantum has been invented, beginnings of 1900s. And there are a lot of applications of quantum now. We are using in everyday life, not like we were talking about the quantum information technology. For example, all the VLSI technology is based on quantum phenomenon in the CMOS circuits. So that's already there. And the science, from the science point of view, it is very easy to appreciate the effects of quantum. For example, the colors of the objects is directly due to the quantum nature of the materials that are considered. And laser is a very common device now. It works on the principles of quantum. And so on and so forth. A lot of examples are there. So when we talk about quantum computers, we say that the computers which use the quantum principles for all the operations that we have been using classical computers. Similarly, a quantum communication link implies that we are transmitting qubits instead of bits from one point to the other. I will elaborate on the more and more on the quantum as we go along. Next one, please. So the starting point has been about 1960s. Richard Feynman was very active during 60s at Caltech, and he has proposed many things. He was observing and commenting on what is possible, predicting what is possible. So this is about 1982 or 83, where he said that we can do computing using quantum effects. Until then, say I know, but by then the transistor and ICs were just the beginning. Transistor were there to get the this, and by 80s, integrated circuits have come and all the electronic components. And the first application that electronics has been put into computing. So preliminary versions of computers were already there and they were rapidly progressing, and people have already foreseen the limitations of classical electronics and computing. So they said quantum effects will limit the computing processes. So the speed of computation, basically in simple words, speed of computation will be limited by electronics. In fact, it is already good actually. You can recall the calculators. We have got, everyone was using calculators in the 80s and 90s. So they were doing very enormous calculations. But from a computer science point of view, if you see, we require much more bigger computing. For example, weather forecasting, or molecular dynamics, or big data problems, or some complex algorithms cannot be handled by classical things. In fact, some of them cannot be solved. Mathematical problems like division of prime numbers, or factorizing a big number into prime factors, etc. Very complex problems, even existing or even in the future quantum computers may not be able to solve. So there are a lot of problems which computationally, I am saying, are very hard, technically hard computing problems. So people are trying to invent newer and newer techniques, particularly by using algorithms to crack this. And Feynman, the first one who said, you have to take a different approach to computing. See, in the electronics world, we use a set of algorithms to solve problems. Suppose you want to sort a list of numbers, you have an algorithm. So Feynman said you have to use an alternative approach. As an example, suppose you want to solve a differential equation. So we know how to solve a differential equation on the computer. You can discretize it, translate matrix form, and all that, and then you can solve this and get the solution of a differential equation. What he said was, why not we use quantum phenomena to solve it? For example, suppose you want to solve the Schrodinger's equation, which is a second order differential equation. You pick up a quantum phenomenon. A lot of quantum phenomena, many quantum phenomena can be reduced to the Schrodinger's equation. So if you want to solve that second order differential equation, you pick up a quantum phenomena, and whatever you observe is the solution to that Schrodinger's equation. So that is an idea that he has envisioned that will happen in the near future. We will not do the classical computing way all the way. With a lot of examples are there, as we go on, we will mention. And he is the first one who has, first of all, identified the limitations of electronic systems, and then predicted that quantum systems can be used for computing. That's the reason why we are talking about digital Feynman. What about this? So this is a brief timeline of happenings in quantum information technology, starting with the Feynman's proposal. Then one of the earliest protocol for quantum communication has come out in 1984. This is called BD84 protocol. Bennett and Resart, two scientists, have announced that protocol. It was said that they have announced it in India, in one of the conferences on nanotechnologies. Then, of course, I will highlight one or two important milestones. First, model of quantum computing. People have envisioned it already in 1985. There's almost beginning days of traditional computing also. Then people have identified some large, big problems which can be solved easily with quantum. One of them is called the Shor's algorithm to factorize large numbers. Those are in security, cyber security, and coding can I easily appreciate. If you are given a very big number, it is very difficult to factorize. If you are given the components, the two numbers, suppose I give you two numbers, very easy to get the multiply and get that big number, but the reverse process is not easy. So this is a factor that is used in security. So each of the parties get a component of that number, and the composite number, while product of that is what is used publicly. So people cannot easily crack that. Of course, that is also depending on the computing power. If you have greater computing power, you can crack bigger and bigger numbers, and then this is only an example. There are a lot of algorithms and examples of big data problems, large computing problems, and so on. Another important algorithm, Grover's algorithm, which is for the searching data. If you have a big data problem, like the Aadhaar card information, you want to search a specific one, is a complex problem. I suppose most of you are using the Google, so you know when you type some keyword in that, almost immediately you are getting some information. But what is happening behind, how complex it is, we cannot assess easily. With a lot of all the nodes all over the globe, information scattered, it is a very complex problem. And a lot of algorithms, a lot of measures like PageRank, which will say how efficiently we are searching, and so on and so forth. Of course, that is extended with the present AI techniques. Many of us talk about AI in our algorithms. So for example, a ChatGPT, if you do some complex problem, it appears that it is doing very quickly. So it is based on the data and all the algorithm. I'm not debating about the fundamental things that AI can do or cannot do. So let us jump to about recent times. 2016 is the time when China has launched the satellite Nicias 1. So they have transmitted quantum key information over 1,200 kilometers from China to Austria in Europe. That woke up many countries. Of course, China has been going ahead independent of, many of us don't know what is happening, because global community doesn't know too much about what is happening in how things are happening in China. But this is one of the first indicators to say that China is going ahead in quantum information technology. And most of the countries have brought in their national programs, including India. So immediately after the launch of that, Indian government has come down to call a meeting of all the people working in this quantum and said, why not we also make a quantum computer? And many of you know that during 2022 budget, the finance minister has allotted a lot of money for the national quantum initiative. So there are a lot of quantum initiatives everywhere now. And at our own level, even a faculty member can easily get into the subject and try to write a project on whatever topic that you are interested. So almost everyone, and also people are trying to relate whatever you know with quantum. For example, our labs has been working on photonics, and we found that photonics is very useful for quantum. We are joining quantum and photonics. Similarly, some groups, they are trying to combine AI and quantum. So quantum has been a buzzword all over the world. So in the recent times, there are a lot of companies like Google, IBM, HP, all these have come into this bandwagon. They want to capture the market as soon as the important developments, as soon as the opportunity comes, they would like to benefit. That's the reason all these companies are into quantum. There's one important difference, I'll put in later on. There's a technological bottleneck, which we compare with VLSI, the developments in VLSI. What is happening is, it is based on silicon. Technology has developed based on silicon, much of it. And silicon is not a suitable material for photonics. You want to build lasers, active components and so on, we have to go for 3-5 materials. So that is about 10 times costlier than VLSI. So it is an important problem that technological people have to solve for quantum to be realistic. That is the most important reason why we don't have a quantum computer now. If you see quantum computer by IBM, or we have QPi labs in Bangalore, go there, it will occupy one room. So many of them are based on superconducting qubits. They will require very low temperature. Atomic systems, Rama Research Institute and some of those people are working on atomic systems. In ISC, since long time, before all this hype, people have been working on molecular NMR techniques. Those are all bulky. Or I'll give another example. If you go to PRL, Ahmedabad, they have full-fledged setup of optics lab, nonlinear and quantum optics. They are all on the table. So all these have to go onto a chip if these have to become reality. If we want good applications, usage in many things, like what all they have been talking about, we need very small devices, room temperature operation, to very little to maintain, and so on and so forth. Let us get going. Very quickly, see, I have avoided mathematics. Of course, we should definitely, depending on the requirement, we should use mathematics, but let me say, the difference between a bit and a qubit. You know, in electronics and digital, we use bits, zeros, and very elementary zeros and ones. 0 is represented by zero current, 1 is represented by a few milliamperes of current, 3 milliamperes or microamperes. So very definite, deterministic. We can exactly measure and say this is 0, this is 1, except for noise and all other impairments. Whereas, when you go to atomic level, we, at least in the present globe, in the planet Earth, we encounter atomic phenomena when you go to, we encounter quantum phenomena when we go to atomic level. You know that electrons have got spin, positive spin and negative spin. We know that photons have got polarization, horizontal polarization and vertical polarization. The most important difference at atomic level is these quantum states, let us call states, that's a good technical keyword, are not deterministic. We cannot exactly say whether a photon is in the horizontal polarization or vertical polarization. We cannot say that electron is in the upward positive spin or down negative spin. But what can we say? It is in some spin, which we cannot measure. As soon as you measure, the state is disturbed. So we have to evolve methods which will tackle the observations without disturbing them. Of course, I will show you a few techniques and systems. So, the state of an object is given by this wave function. This is called a wave function, psi. And it is not deterministic. So, what can you say when it is not deterministic? It is random. The probability is assigned with psi. Let us assume, for understanding, let us talk about polarization of the photons. So, what is the angle at which the photon is? Arbitrary, you don't know, but it is there in some state. And you also know that it can be horizontal polarization or vertical polarization. I can define horizontal polarization as 0 and vertical polarization as 1. Once again, if you are talking about single photon, this horizontal polarization is not well defined. Only probability of horizontal polarization is so much. Probability of vertical polarization is so much. And you can represent the arbitrary polarization psi in terms of horizontal polarization and vertical polarization. Simple linear algebra. 0 and 1 are the basis functions. Linear combination of that will give you the actual polarization. Now, it is not only polarization, it is not only probability. There is a probability distribution function. If you say an object, the photon is in the horizontal polarization, probability of 0 is something, probability of 0.1 is something, minus 0.1 is something, and you have a probability distribution function around that horizontal polarization. Similarly, there is another probability distribution around vertical polarization. And the linear combination of that will give you arbitrary polarization. So how do you measure, how do you tackle this? In random process, use the mean and standard deviation and all these moments to describe these PDFs, probability distribution functions. So 0 ket. This notation is called the ket notation, represents the mean of the PDF. 1 ket is the mean of that vertical polarization. And the actual polarization, the mean is this. That means we know behind that is the PDF. And actually, these are not PDFs. Psi is called a wave function. So square of psi is the probability. That means you have to go back to the quantum mechanics. You have what is called this Schrodinger's equation, representing many. See, this is one of the models. There is density matrix formulation. There are so many operator theories. So one of them easiest to appreciate is the Schrodinger's equation. So solving Schrodinger's equation for the given conditions will give you that wave function. Square of that wave function will give you the PDF. So you have a 0 ket and 1 ket, mean of those, and a linear combination of that will give you psi. Why this explanation is needed is, Schrodinger's equation is only complex thing. The result psi is a complex number, complex function. So alpha and beta are complex numbers, not real numbers. So what is the implication of that? The state of an object, polarization, is represented by a linear combination of deterministic, not deterministic, the real vectors in combination with the complex coefficients. That means there is a phase. You can interpret that as a phase of the polarization. It's not exactly phase. It's an important difference that mathematically if you go, you can get it. So alpha into 0 ket plus beta into 1 ket with alpha and beta as complex numbers. Just as to extent, if suppose the photon is in the 45 degrees polarization, we don't need complex numbers. 1 by root 2 of 0 ket and 1 by root 2 of 1 ket will give 45 degrees. What is the implication of complex numbers is important. I would like to mention, see when we study mathematics, we actually go from natural numbers to rational numbers, irrational numbers, real numbers, and then to complex numbers. And we say that complex numbers are needed to solve the equations of this sort of x square equal to minus 1 and so on. That means complexity is a real phenomenon. Phenomenologically, if you take from quantum point of view, the real world is a complex system. So in fact, if someone is interested, we should go on to Hilbert space. Points, these are all the functions and all these states are points in the Hilbert space. That much about the quantum. So the point that I want to drive here is alpha and beta can be complex numbers. And alpha square plus beta square, the total probability is 1. So due to this complex nature, a lot of interesting things are coming up in the quantum world and Fourier systems. We can represent the states of the quantum object on a Bloch scale, what is called Bloch scale. And 0 ket and 1 ket are the basis vectors. As simple as that. We can also put it in polar coordinates. Let us get that much about the nature of the state of the object. So we want to go for many qubits. Think like bits, we want to transmit several bits. We want to operate with higher bit computers and so on and so forth. So 0, 2-bit system, 2-qubit system. If you want to talk about, we should have 2 different objects, 2 photons. First photon, second photon. Each photon has got its own state and its own basis and so on and so forth. So you have a joint probability distribution. Instead of having a single distribution function, you have a joint PDF. So you have 0, 0, 0, 1, 1, 0 and 1, 1 ket, independent. I am not saying whether they are correlated, not correlated and all that. Generally, so and you can represent by ket of 0, 0, ket of 0, 1, ket of 1, 0 and so on. That is about the 2-qubit system, and the actual state of the 2-qubit wave function is a linear combination of alpha into 0, 0 ket, alpha 1 into 1, 1, 0, 1 ket, alpha 1, 0 into 1, 0 ket, and alpha 2 into 1, 1 ket. So 4 basis vectors are needed for a 2-qubit system. That means if I have an n-qubit computer, quantum computer, the basis is 2 power n vector. That means the quantum is scaling exponentially. This has got the most important implication on computing. If you want to build a quantum, if you want to build a computer of 1000 bits, suppose you have a bus, computer bus of 1000 bits. We need a quantum computer of only 10 bits, qubits. Many of us calculate the computational complexity. You know, how many atoms are there in the universe? And if you want to represent all the possible qubit states, how many are needed? So people estimate that around 10 power 80 is the number of atoms in the universe. 10 power 80. That's a very large number. But number of qubits needed to address 10 power 80 states, physical states, is only 2 power whatever, 80 to 3. Suppose I assume 10 is 2 power 3. 240 qubit system is sufficient to, of course it's very possible to use up all the atoms in the universe, but only 240 qubit quantum system is sufficient for such a complexity. That's the order of magnitude. People estimate, suppose you are trying to estimate the Aadhaar card information problem, solving Aadhaar. So 140 crore people, suppose you calculate what is the quantum complexity of the quantum computer needed for that. Very crude estimates. Let us get going. I'll show you a few gates. Now we should go faster because we will not have time for once. So I'm showing some gates. You can consider gates as input-output functions. X is the input, Y is the output. The matrix is representing the transformation operation. You can, whatever we have seen earlier, the basis functions and so on, you can translate into matrix form. Okay, input outputs can be translated in matrix form. Say for example, of course I have used up X for the polygates, but suppose if there is input X1 is the input qubit, Y1, Y2 is the output qubit, then 0, 1, 1, 0 multiplied by X1, X2 is the output. You can easily identify this is not operation. The first one X is not operation. But I have put two strange operations. 0, 1, 0, 0 minus 1. And the middle one is still stranger, that is a complex number. Because this is allowing, quantum phenomena is allowing us one complex numbers. Let us get back another one, another gate. 0 qubit is the input and output is 0 plus 1 qubit state. So it is you can think of it as translating into 45 degrees or minus 45, other one is minus 45 degrees, and the H1 and 1 minus 1 is the matrix for the other one operation. So it's a very strange thing that doesn't exist in the classical digital logic. And there is no proper representation beyond a certain complexity. It's very difficult to graphically represent. Yeah, let's get going. I hope I'm I am not too much to mathematical aspects of it. So there are a lot of presentations. If someone is familiar with QSKit, it's very simple, all these things. Okay. There's a good tool from IBM. QSKit can solve all these gates and all these systems problems. So this is called a C0 gate. C is the control port, T is the signal port, and this T operation C is the output of C0 gate. You can see, you can appreciate this from this matrix. 1, 0 and 0, 1. When C is 0 qubit, T operation C is identity, pass-through state, no change. And when C is 1 qubit, 0, 1 and 1, 0. So T operation C is NOT gate. So you can get a NOT operation based on the value of C. Similarly, double C0 gate. There are two control ports, and I think that matrix is not here. You have an 8 by 8 matrix. When both C1 and C2 are 0 qubits, T is passed through, and when both C1 and C2 are 1 qubit state, C is a NOT gate, and all the intermediate states are possible. Let us get going. So I think we should go faster now. So this is NAND gate. People are considering in digital logic, you know that NAND is a universal operation. Most of the gates we can reduce to NAND operations and then build the logic circuitry. So similar thing people are exploring, which could be a ideal universal gate. So it need not, NAND is not sufficient because it is not including all complexities. So people are considering C0 or some other. There are several models, several algorithms which use different. There is no standard quantum logic circuit. One more please. So now if you want to build a complex quantum information system, what are the different criteria? These are called the dimensions of criteria, announced long ago in around 2000. So you need to have a scalable physical system. That means if you are operating the few qubits now, we should easily be able to extend it to n number of qubits. May not be large, may not be possible, but say 100 or more than that. Similarly, you must be able to initialize the state of the qubits. As I said in the beginning, we cannot know exact state of the qubit. You cannot copy. That's one of the theorems actually. No cloning theorem is called. You cannot copy the state of the qubit. As soon as you interpret that, that is gone. Without looking at that, you have to do many of the operations. There's an important phenomenon called entanglement. You can create qubits which have correlated properties. For example, if the first photon is in the horizontal polarization, we can generate second also in the horizontal polarization simultaneously, or the opposite. So using entanglement and some such phenomena, you can do many operations. We can interpret the quantum information functions. Then decoherence is an important problem. The quantum states doesn't remain there for long. A small fraction of the seconds or a few seconds they can remain in the same state. They will change. So that is going to be a problem. If you have to do computations within that short time. You have to design quantum information systems which will have low decoherence or higher decoherence if needed. And we talked about universal set. Similarly, measurement capabilities are also defined in terms of the operators and so on and so forth. Let us get further going. Next. Okay. So let us get going. So I think we have to, I will give these slides. These all papers are there for whatever you are interested. This is only a initial talk in the conference. So we'd like to show you a few recent developments and then wrap up. But this is one comment for each slide I'll make. So this is how you design the quantum computers. Use a layered approach, like what we do for transferring files on the internet. You have the 7-layer OSI model, starting with physical layer, data link layer, network layer, and so on to application layer. Similar approach is followed for designing present-day quantum computers. Next one, please. So this is the sequence of steps involved. One of the important things somewhere is written is simulators. Nowadays there are a lot of simulators are there which can be used to replicate what happens inside. In fact, they are all semi-classical, semi-quantum, not fully quantum. We can use the existing traditional computer to simulate to some extent, but you need a real quantum computer to simulate fully quantum operations. Next one, please. I'll show you one algorithm to represent quantum communications. So if you want to do quantum communications, you need to have all these devices, like source. You need to have a single photon source or single qubit sources, high-speed photo detectors. We have to study we can use either the optical fibers or free space optical communication for transmitting quantum information, and also many other things. And also I have put one point in the end. In the universe, how is communication going on? See, we feel that human beings are the ones who have invented communication and we are doing communication. But communication is going on in the universe, extraterrestrial. For example, if there is a planet somewhere and a galaxy somewhere, there is interaction between them. How is that communication going on? It's called the deep space communication. That's one form of deep space communication. People feel that all this communication is going on the gravity, through gravitational waves, and in particular quantum gravity is an important development in science in the recent times. So let us get going. Okay, let us, one small example I have taken of QKD, quantum cryptography. Alice is called the transmitter, Bob is called the receiver. They have a quantum channel to transmit the header information, and there is a public channel for the data. And Eve is trying to disturb this quantum channel, try to steal the information and all that. That is the setting. So I will just describe this BB84 protocol. Let's get going, next one. So this picture really represents what happens in a BB84 protocol. Okay, you have Alice here, Bob there, and this is the bulb can be representing the source of qubits. And qubits can be, as we described earlier, they can be in the basis states can be 0 Sept and 1 Sept, horizontal polarization, vertical polarization. Alternatively, another basis can be plus 45 degrees and minus 45 degrees. So in this BB84 protocol, Alice has the choice to choose either the first basis or the second basis randomly. So when the qubit comes, she can choose 0 Ket 1 Ket combination or minus 45 degrees plus 45 degrees combination randomly. Okay. Then similarly at the Bob, on the receiver side, Bob also has two options. One is horizontal vertical or minus 45 degrees plus 45 randomly. So we have to work out all the combinations that are possible. A 0 qubit is sent by Alice using the first machine, detected by second machine by the Bob randomly, unknown to Alice, and so on and so forth. So here I have put all these combinations. That means they are trying to make a lookup table. When the actual data comes, they will look at the table and say this is what has been sent. So if you work out, just as an example, I have put 1100, etc. By these are the states of Alice, these are the states of the basis vectors of the Bob, and this is the received outcome, and we are checking whether this particular combination is possible or not. So what we observe is 50% of these entries are not correct in this protocol. If they do, if Alice does randomly, Bob does randomly, and this basis. So, if of course they will have to agree, they have to compare, they have to exchange the table, they have to have the table and exchange the algorithm, and then that proceeds. Now, Eve wants to disturb this one. What she does, she gets 4 machines, 2 for transmitting, 2 for receiving, and exactly same what Alice and Bob are doing. She also does randomly, and then receive and transmit. So we have to work out the table, double the table of this. What Alice is doing, what Eve is doing, what Bob is doing. So you have a bigger lookup table, and Alice and Bob unknowingly, if they compare their tables, what do they have to find? Only 25% of the entries are correct. Unknowingly, whether Eve is not there, whether it's there or not, they don't know. So they find only 25% of the entries are correct. So that means the communication link has been compromised. That's what provides the inherent security of this quantum communication protocol, BB84 protocol. Nowadays there are a lot of new protocols like E92 and so on and so forth, which give much more efficient, much more easy to implement also. And this BB84 itself is used as an example, and people have translated onto devices, onto a chip and all that. So I hope this will just let us get going. Next one please. Some more few slides before we conclude. These are missions on satellite by Chinese, and then they are continuing. A good amount of research goes on in China. Okay, let's get going. Next one please. Next one, please. Now it will be faster because we are getting closer to all stories only, no fundamentals now. So there is an idea of what is called the quantum internet. You know, we have a big internet all over the globe. Nodes are distributed, and you do all the communication and transmission of information and so on. So if you have quantum information, how do you do it? It's an important question. And a conclusion you can say is that the probabilities or the PDFs are distributed across all the nodes. We can say quantum information is distributed simultaneously across all the users, but not to any particular user specifically. So based on that, a lot of developments are there in quantum internet now, and people feel that it can be a very, very almost instantaneous communication at the speed of light. No propagation delays at all these memories, and so on and so forth. There is. So next few slides are photonics. One single comment that I made in the beginning is applicable now. Much of our integrated photonics technology is based on silicon, and a few other materials like carbides, nitrates, and are useful at this moment. And in the future, we expect indium phosphide 3-5 materials. And as a stopgap, we have materials like lithium weight, KTP, and so on, which have got very good electro-optical and nonlinear optical properties. These will be very useful for creating a lot of quantum information functions. One more please. So let's skip to almost towards the end. But at least one slide I want to show about our work. Yeah, let us get going. Yeah, a lot of important devices that if someone is a photonics engineer, maybe you will be familiar with many of the devices that are there here. Like you see the ring resonators here, and these are all used in traditional photonics, but they can be used to do quantum information functions. So you have gratings, you have double ring resonator to generate the single photon source, and so on and so forth. You can do a lot of signal processing also on the chip. These are all integrated. We have talked about integrated, not bulk. Somewhat, almost towards the end to our work. So good papers are there for those who are interested to learn about photonics. Some more, one more please, next one. So you require a lot of devices. I would like to mention, India is nowhere in devices yet. Only recently we have got the VLSI programs in India, and it's a long time before we can manufacture optical devices and photonic devices. Let us get going. Next one please. One more. Yeah. You can do a lot of quantum signal processing. Next one. So people have done some of this. That's what is this is from nature communications and all that. Let us get going. One more please. Still further. QKD people have done on the chip. They have evaluated if you want to do QKD on the chip. Some more please. Another one. Yeah, I will go to one more by our labs slide if it is there. Next one please. Yeah, some more. All photonics you can skip. So, a lot of interesting things I have put here, but I have not described, like teleportation, entanglement, and all are interesting phenomena. So, a little bit about our lab. And even now, we work a lot on theory. Some of our students have done on counterfactual cryptography. A few quantum algorithms translated into photonics form, integrated form, and so on. Next one, please. Yeah, this is one of our recent work called higher dimensional key distributions. Instead of having only 0 and 1 states, you can use intermediate states, like multi-channel communications. You can have in-between states, and you can achieve very good, higher efficient quantum information functions. Let us get going. One more, just back to one. See, I have been talking about only polarization until now. We can use angular momentum of the photon. It's a very efficient, very interesting parameter for quantum information functions. Just one more, this is almost final slide. See, as you know, in our lab, some of you who are familiar with our activity, we work on integrated devices like this Y branch. This is property of a Y branch. Ring resonators, gratings, directional couplers. These are all the traditional integrated optical devices, passive devices to some extent. And you can translate them into active devices by using electro-optic effect, non-linear effects, and so on and so forth. Here I am taking an example of a Y branch to show what happens if you use it for quantum functions. So one of the ideas that we have is, instead of using the polarization, we can use the modes, T mode, TM mode, T01, etc. Modes of the optical waveguides to represent the quantum states. And it is very easy to extend it to HD. I can make a 4-mode waveguide very easily. 8 mode also I can make very easily. Simply by changing the bits. So we can easily implement higher dimensional quantum information functions. In this example, this is a 2-mode waveguide having T01 and T1 mode, and you can observe that the output of this can be represented as a linear combination of 0 ket and 1 ket. 0 ket minus 1 ket. If you recall in my earlier slides, this is a quantum Hadamard operation. Conventionally, what you feel, a Y branch will simply divide the power across 2 output ports. If you launch a single photon, the photon cannot be split across first port and second port. The output of this can be considered as a linear combination of the 0 state and 1 state. That is nothing but Hadamard operation. This is one of the things that we demonstrate one, and that is the photonic band gap structures used to implement this Y branch. So photonic band gap structure will be very small compared to a Y branch. Y branch typically has got a very small angle, and so it's very long. It's not very convenient. Silicon people are not very happy with such devices. So they are very much interested in silicon real estate. We have to use the chip area very effectively so that we can make lot of compact devices. Let us complete. One more, next one please. So this is another work by one of our colleagues, Professor Varun Raghunath in our department. They are trying to generate single photon sources by using ring resonators, optical waveguides, and so on and so forth. Next one please. Yeah, that's all almost towards the end. This is our group, slightly older one, but many of our people are here. Next one. 3 slides I will show you about our activities. So this is our alumni, 3 slides I have put. Kalora has worked on previous one, this very brief description. He has worked on quantum algorithms, and he has produced good papers on control of atomic spins and so on and so forth. Next one please. Akshara has worked on random number generation, which is a very efficient way in quantum information, cryptography, and a few information processing functions. Then next one, Bhavani has, next one please. Bhavani has combined, which many of our students are interested. He has combined quantum with machine learning algorithms. We take a CNN algorithm or Fourier transform, quantum Fourier transform, and translate how it can be implemented using photonics. So all these papers are available for those who are interested, and I think I will conclude at that. Thank you very much for listening. We can take some questions.
So one question is that the QKD chip is already in SOC they have done VLSI. It is realistic. It is possible now.
QKD is the hot subject in quantum information technology right now. So many implementations are there now. Very efficient implementations are on the bulk, on an optical table, on a bulk system, even small one like a suitcase sized bulk optical QKD systems are available now. And in the long term, people want it on the chip. I have shown some picture where QKD is implemented on silicon. Except that source detector and quantum, qubit sources and all will be outside the chip. They are hybrid, integrated, and QKD systems are available now.
Any other questions from the audience? Any questions? Thank you, sir, for your distinguished presentation and valuable guidance.
So I will request, I thank you very much for inviting me to your conference, involving me in your conference. I will request some of the members who are present here to join IEEE Photonics Society. If you want to work in quantum information technology, Photonics is the correct route. Thank you.
Thank you, sir.
And if you don't have a, see, I know some of you are there from other institutions. So if you want to start the activities, start a student branch or Photonics Society chapter, please get in touch with us. We'll help you to do that.
Thank you, sir. I request all the participants to have lunch. Following the lunch, the panel sessions will be resumed, and the participants are requested to attend their paper presentations to the scheduled time and venue given in the prospectus.
Tell them. Mathematics is important for AI.
Yes. Correct, sir.
And rigorous mathematics, not simply superficial calculations. You want to
Thank you.